Hi, in this video I would like to introduce you a very general useful skills in physics, and you can transfer it in all chapters in physics. Even you may also apply it in other subjects as well, including maybe economy, finance, chemistry, and other subjects as well. The name of these skills is called dimensional analysis. So you may find this sounds very sophisticated because I feel the same as well when I first heard it. So the purpose of doing dimensional analysis would have two reasons. One is to deduce the unit of a certain parameter, or you can use this approach to check the validity of an equation, which people may call it dimensional homogeneity. So let me show you an example. In the one of the equation that we will learn in the future, that is BIL in chapter 5. This is referring to the magnetic force that one current carrying wire would experience. So if you still remember what probably you have learned in IGCSE, when you have a wire running with current, and if there's say some sort of B field, magnetic field running through it, then there will be a force, right? You can use the hand rule to figure out the direction. So here is the equation to calculate the amount of the force. So F is obviously the force, B is the magnetic field strength, so how strong the B field is. I is the current, and L is the length of the wire that experiences the B field. Okay, so what I would like to do right now is, since probably you don't know the unit of B field, so what you can do is to simply use the dimensional analysis to work out the unit. And so the idea is very simple, that you just have to rearrange the formula like so, and so you can find out the unit of B, which is the magnetic field strength, will be the same of course as the unit of F over IL, and that would equals to, just you recall each of these components unit, and that is Newton divide amperes and meter. Okay, so that is to say, if you really don't know the actual unit, actually there is a unit for B field, like the magnetic field strength, which is actually T, which actually stands for Tesla, right? Obviously, because Tesla worked really hard on towards the magnetic electromagnetism. So that is why the unit is named after him, Tesla. So T precisely. So in case you somehow don't remember the unit of B, which is again Tesla, then what you can do is to express this one instead. Okay, so you can express Newton per ampere per meter. Alright, let me give you a question to see whether you understand or not, so you can practice on it. In gravitation, which is another chapter that we will learn later on, there's an equation called F equals to big G m1 m2 over r squared. So this is an equation describing the gravitational force. So let's say there are two planets, which of mass 1 and mass 2, and their distance from center to center, which is their center of gravity, will be r, and G is something called the universal gravitational constant, and F is of course the gravitational force. So my question obviously is, I want you to find out the unit for G. Right, so can you use the dimensional analysis skills to help me to find out? Pause the video, try it now, and we'll show you the answer.
A few moments later.
Alright, so what you simply have to do is obviously rearrange the whole equation with G as the main term. So we will have F times r squared over m1, m2, right? M1 and m2 is just two different mass, and then we'll put a bracket to express, we are talking about the unit, and so that should be Newton times meter square. Okay, not to confuse meter with mass, and then kg down below will have square. So to express it nicely, then I can rewrite it like this. Okay, so maybe we can check the data booklet as well to see whether or not I'm doing it correctly. And the answer is yes, right? It's Newton meter cube per kg squared. One useful way of applying dimensional analysis is to check the validity of an equation. So that is to say, there are times, for example, when you are doing your internal assessment, your IA in the future, you may find out there's no literature review talking about the thing that you are studying. So when you try to collect the data and propose a new equation of the relationship of your IV and DV, then one thing you can do to ensure that is at least in terms of dimension is appropriate, then you can check its unit. So for example, if someone is trying to argue that, hey, for the elastic potential energy, as we all know, it's half kx squared, of course, but let's say someone is arguing, oh, that is actually cube instead, all right, x cube instead. So how can you actually counter argue this statement? So that is by using dimensional analysis. So let me show you an example here. Alright, so we all know that the unit of energy is joule, and if we want to derive with the base SI unit, actually we did earlier, we can actually use the formula of work done, which is force times the distance s. So that actually means that joule would equals to Newton, or actually F equals to MA as well. So let's do MA. So kg meter S -2, and also one more meter, so m squared. Alright, so this is on the left hand side. For the right hand side, what we will have is for the unit of half kx cube, what that student proposed, then we will have k, cos k you can relate it to the Hooke's law, that is F equal to kx, and so k will be in Newton per meter, or cm, I guess meter is fine. So we would have again Newton as in F equal to MA, so that would be kg meter S -2 and divide m, and so that's why the m is gone, and then you have x cube here. So x is the extension, right? So that will be meter cube. So if you try to compare these two, they both have kg, they both have S -2, but then in terms of the meter, here you can see it is square, and here you can see there's a cube. So in terms of dimension, they don't even match. And this is a huge problem, because when your dimension doesn't even match, you can't compare them, right? And you can't even provide a equal sign on the two sides of the formula. This is like what we have talked about earlier about in the disaster about the Air Canada, if you remember. They somehow mistook the volume with the mass, right? Liter and kilograms. You cannot compare it, right? You can't say 100 liter is more than 50 kg. You can't say that, right? So because they're simply in different dimension. So doing the dimensional analysis can help you to verify or validate an equation. However, if the dimension match doesn't mean it must be correct, right? You have to think about the logic behind. Okay, I'll say it again. If you find out the unit doesn't match, so like this one, we find out the unit doesn't match with what we understood, then for sure that this equation will be wrong. But in the times where you may find the unit, both sides of the equation will match, doesn't mean that the equation must be correct. Alright, so the logic is, I guess, is somewhat like your mom is a woman, but all the women doesn't mean they all are your mom, right? So logical statement. So the other issue with dimensional analysis, or the limitation, would be they would not be able to tell you whether or not the constant number, those dimensionless parameters or numbers in the equation will be valid or not. So for example, if you think about the actual equation of elastic potential energy, is again half kx squared, right? So if someone just propose, hey, what if I say the elastic potential energy is just kx squared, then if you try to use dimensional analysis, it is fine, right? It passes the test. But passing this test doesn't mean everything is good. So this is a tool for us to use, and you have to understand its limitation. Lastly, there is a question involving dimensional analysis from the textbook. So I would like you to do it. So pause the video, try yourself, and we'll talk about how we should do it.
2,000 years later.
In case you don't understand the question, let me try to clarify with you. So one thing that you must know is C is given that to known as a dimensionless constant. Dimensionless means there's literally no unit attached to that number. So one example could be pi, obviously, but more physically, there's also one thing that you have learned. I give you 5 seconds to think about it. One of the examples that I can think of is refractive index n. If you can think of others, of course, please leave the comment below. So for refractive index, if you recall the definition, it is C over V. So that is the speed of light in vacuum divide speed of light in a particular medium. So in terms of unit, it is meter per second divide meter per second. So they just cancel out. So that means there's no unit for n refractive index, and that's why n is one example for dimensionless unit. Alright, so this is something that you have learned before. So for this question, other than knowing C is dimensionless, we also are given this as equation. So what we can write is just simply copy it right here, and then since they are valid, I mean we assume this equation because it's given to be valid, then we can say the unit should be balanced. So this is how you can apply dimensional analysis, and just referring to each variable, and we would like to turn them into the base SI units, because like you have learned in the beginning of this chapter, all of the variables, all the parameters, you can express them with base SI unit. That's 7 base SI units. So for frequency, it's actually 1 over period, so that is S negative 1. And for C, because this is dimensionless, we just forget about it. As for M, which is referring to mass, then simply kg. And here we have to put x in the index because we don't know what x is at this moment. So it could be 2, that means it's mass square. So in terms of unit, it will be kg squared. Or if it's other number, then yeah, then we just keep it there. As for k, it's a bit more tricky. So let me just deduce it again, although I just did it earlier. So for k, it is the spring constant. So we can recall it with F equal to kx. We arrange it to get F over x. And so we know the unit of this will be same as F equals to ma, so same as kg meter S negative 2 divide m, because x is in terms of length, so m will get cancelled out. Yeah, so same as what we did earlier. And so here we will firstly express k as in kg as negative 2, but there is a index of y here, so we'll keep y outside. And so now we can finally compare the two after we expand it. So let me just expand it first. So we will have kg, let me just show with a better color. You can do the same as well. Kg to the power of y s negative 2y. Alright, I assume you know how to expand this. So it looks very nice. So what to do next is to simply compare their index. If you have ever learned about something called complex number in mathematics, then you may find this is somewhat similar. So what you have to do is simply comparing for s on both sides. So this is -1, and therefore that should equal to -2y, and then we compare kg. So on the left hand side you don't see any kg, so what you can do is you can think of there is kg, but it's in the power of 0, because that is nothing, right? So on the left is 0, on the right hand side you got x and y because you multiply, alright, and then you turn that to plus in this case. So eventually you should be able to deduce. So this one obviously tell you y equals to 1/2, and then since y equals 1/2, then x should equals to -1/2, right, to solve this equations. So at the end, if you simply substitute this back to the equation here, I don't have space, maybe I can write here, then we can actually not this one, back to here, then we can have f, therefore f equals to cm -1/2 k 1/2. So if you like to express nicely with the square root, then basically that is what you can see from the question here. Okay, so this is a very interesting question. So I hope you enjoy learning dimensional analysis, this skill in physics. I hope you can use and apply these skills in all other topics you see in physics in the future, and maybe in other subjects as well. It will be very, very useful.